In this video, let's move on to the next learning objective, and that is, what is white noise? So white noise, think of it to be some kind of an error or shock term, and we represent it as epsilon sub t. You can think of white noise to be like a time series equivalent of the error term that we encountered in the chapters on linear regression. So if that error term was for cross-sectional data, this epsilon sub t is meant to be for time series. You can think of this epsilon sub t to be, let's say, the unexplained kind of change or shock in yt, the time series which we are trying to model. So therefore, this white noise is a very important building block when we write down any model that is meant to explain the dynamics of any given time series. Okay, so we will encounter this white noise in all the models that we will kind of study in detail. Okay, what are the properties of this epsilon sub t? The first property is that it has a constant and specifically a zero mean, which is to say that the expected value of epsilon t is equal to 0. This mean of 0 has been chosen purely for the purpose of convenience. Okay, then the variance of this epsilon t is also constant and it is finite, and we denote it as sigma squared. And then the third property is that white noise is serially uncorrelated. What that means is that if you were to write down the covariance of epsilon sub t with epsilon observed, let's say, h periods back, which is epsilon sub t minus h, then this covariance, it turns out to be 0, and because this autocovariance is 0, the autocorrelation is also equal to 0. So we say that white noise is serially uncorrelated. The reason why we have imposed this condition on the white noise is that we want the autocorrelation of any time series yt to be purely driven by the chosen model parameters of that time series. We don't want the autocorrelation of time series y to be in any ways determined by the autocorrelation of the epsilons. Okay, so we will see that this property that my white noise is serially uncorrelated comes in very handy when we write down the autocorrelation function of any time series that we study. Okay, then in terms of notation, then I can write down that epsilon t is white noise with zero mean and variance sigma squared. Now you can very quickly check that these three properties which we have specified for our white noise make white noise a covariance stationary kind of process. Okay, it has a stable mean, condition 1 satisfied. It has a stable autocovariance structure. See, autocovariance does not depend on t, it is 0 always. And number 3, my variance is stable and finite. It's equal to sigma squared no matter which t we are referring to. Okay, so all three conditions satisfied, white noise is covariance stationary. Now, when we impose the uncorrelated kind of assumption on white noise, we are basically referring to weak white noise. Why? Because we know that uncorrelatedness is actually a weaker condition as compared to independence, right? So therefore, what I can do is that as an extension of what I have just studied, I can define something called independent white noise. So in independent white noise, instead of me talking about uncorrelatedness, I talk about independence of successive epsilon t's. Okay, and I can therefore say that independent white noise is strong white noise, and I represent it, as far as notation is concerned, as epsilon t is IID with mean 0 and variance sigma squared. Okay, so this is my second kind of white noise. There's a third kind of white noise as well, and that is Gaussian white noise. So go back to the way I defined white noise. Now, in this first weak white noise, I didn't even specify what is the distribution of epsilon t. All I said was mean 0, variance sigma squared, and serially uncorrelated. Okay. Now, when I come to this third type of white noise, the Gaussian white noise, I am also specifying that epsilon t is coming from a normal distribution. But again, mean 0, variance sigma squared. Now, in this world of the normal distribution, there's only one kind of dependence, and that is linear dependence. Therefore, the uncorrelatedness assumption is also implying the independence assumption. It's one and the same thing in the normal distribution world. Therefore, Gaussian white noise is both uncorrelated as well as independent. Okay, these are three types of white noise. Now, before we move ahead, let's very quickly, get used to this measure called the conditional mean and the conditional variance. Okay, now conditional, this aspect of mean and variance is basically that when I compute a conditional mean, or for that matter a conditional variance, I have to take into account the information that has been recorded till a particular point in time. This information that, let's say, recorded up until this time index t is denoted by this very fancy kind of f subscript t. Okay, so think of this to be all recorded values of your time series up to and including the observation at time index t. Okay, so going back to that example that we were following in the first video, the example about how stock prices behave on an intraday basis. Let's say if I were to ask you what would this be, that means let's say this would basically be the set which contains, let's say, elements which are y0, y1, y2 and y3. Okay, this is like an information set which contains all observed values of the time series up to and including the observation corresponding to this time index, which in this case is 3. Okay, now when we have this information up until a certain time t, it's like intuitively it's like I am placing myself not at 9:30 a.m. the start of the trading day, but rather I am placing myself at 9:45 a.m. Remember, every time index was spaced at 5-minute intervals, and therefore it's like saying that I am placing myself at 9:45 a.m. and therefore I have already observed 4 observations of my time series. The one at 9:30, 9:35, 9:40 and 9:45. Okay, so when I define the conditional mean, it's basically the expected value of the y that will be observed at the next time instant, which is t plus 1, given I have the information about this time series up to and including this time index t. It's like saying, what is the expected value of my stock price at 9:50 a.m. given that I am standing at 9:45 a.m. Okay, so this will be different from the expected value of my stock price at 9:50 a.m. when I am standing at 9:30 a.m. Okay, when I have no, let's say, information at all. Okay, now this is the conditional mean. How would you sort of apply this definition of the conditional mean to this time series y sub t, which is purely composed of white noise? So yt is equal to epsilon t. So this is what I am after. This information, what will it be? It will basically be the set containing all recorded values up to and including this time index t. That means epsilon t minus 1, epsilon t minus 2, and so on. Okay, all these epsilons have already been recorded. Now, when we make this assumption that these epsilons are serially uncorrelated and in a stronger sense serially, I should say, independent, therefore this recorded set of values of epsilon will play no role whatsoever in finding out the expected value of the epsilon in the next time instant. Okay, so therefore this guy does not give me any meaningful information, and the conditional mean in the case of white noise is equal to the unconditional mean, which is simply the expected value of epsilon at t plus 1, and this we know is equal to 0. Okay, because expected value of epsilon at any time index is equal to 0. Now, let's move on to conditional variance. Very simple. This is simply the variance, but conditional on this fact that you have available with you recorded information about your time series up to and including the time index t. Same formula as we have for the variance, but every time we compute the expectation that is going into this formula, we, instead of using unconditional expectation, we work with conditional expectation. Okay, same formula, but we switch to conditional expectation. So this and this, all you have to do is you have to compute these expectations based on the available information. Let's apply it very quickly to white noise. What do we get? Variance of epsilon t plus 1 given you have recorded information till t would be equal to the expected value of epsilon t plus 1 squared given I have the entire information till t minus this guy, the whole squared, and this we know is 0, so 0 squared. Okay, now I know that the variance of epsilon t is equal to sigma squared. This I know is the expected value of epsilon t squared minus the expected value of epsilon t the whole square, which is 0. Okay, so the expected value of the square of this white noise is sigma squared. Okay, now again I know that because I am talking about uncorrelatedness and in a stronger sense independence, this guy carries no information whatsoever for computing this expectation, and therefore I can write it as very simply sigma squared, same as the unconditional expected value of epsilon squared. Okay, so what does it tell me? It tells me that the conditional mean and the conditional variance of white noise is exactly the same as the unconditional mean and the unconditional variance. Therefore, when it comes to just the white noise, a time series something like this, is actually useless in terms of forecasting. Why? Because all the effort that you employ in building this information set of recorded values up to and including time index t is useless in forecasting the epsilon t over the next time step. Okay, so therefore this for models which purely contain this white noise, they are actually quite useless when it comes to forecasting. So what we want going forward is to look for models in which recording this information up to and including time step or time index t does give us some benefit in terms of arriving at the forecasted value or the expected value over the next time index. Okay, so this video was about understanding 3 types of white noise. Weak white noise, strong white noise, and the third one was Gaussian white noise, and then understanding what is the meaning of conditional mean and conditional variance.